I am part from the Wolfram Quantum Framework team. Now, let's start with the presentation on hybrid optimization for variational quantum linear solver. Okay, so for this presentation, we will talk about hybrid optimization, in specific, the quantum natural gradient descent. My goal with this presentation is to guide you through the Wolfram Quantum Framework functionalities and how to apply them into your own projects. For that, I introduced in this presentation the quantum linear solver algorithm, which I will use as example. So we can use the quantum linear solver algorithm along with the quantum natural gradient descent. So let's start. Before going into the domain of the quantum realm, let's first understand the theory behind the gradient descent optimization method. Gradient descent algorithms are techniques used to find the minimum of a cost function. To briefly explain it, we can use these illustrations to visualize how the optimization process looks like. Given a cost function, we can generate a contour plot of its values in many layers. The lighter the color, the higher the value will be. The process goes through steps, and we can visualize them as vectors going to the minimum value, as we can see in this picture in the left. So what's the difference between the regular gradient descent and the natural gradient descent? When we're working with the regular gradient descent, we assume a flat or Euclidean parameter space. The step, as you can see here in the equation, is given by the learning rate eta and the gradient of our cost function. So the algorithm won't take into account the geometry intrinsic to the cost function, which would lead to an efficient search of a minimal value. Okay, so if we want to take in account the geometry of our cost function, we can generalize the gradient descent into the natural gradient descent using the metric tensor F. Well, to be precise, we use the inverse of the corresponding metric tensor to correct the gradient direction. As you can see in the equation here, this would lead to an improvement in our optimization. So what happens when we have a quantum optimization problem? When using a quantum variational algorithm, we will face a similar problem. In this case, the parameter space is defined in the space of quantum states. The metric we are looking for is called the Fubini-Study metric tensor. The Fubini-Study metric is a way to measure the distance between two quantum states, helping us understand how different or similar they are. For qubits, you can picture it as part of the way we understand their movement in the Bloch sphere. So now that we understand why we're using the quantum natural gradient descent, we can talk about the cost function that we are going to build now. In this case, we will define our cost function using the fundamental process of the variational quantum eigensolver, which given an answer circuit B, we generate a variational state that we will use to implement our cost function as mean energy or mean value, as we can see here in the equation. So the idea behind this is to repeatedly adjust theta, the parameters theta, such that we minimize this cost function. So now that we have reviewed all the important stuff from here, we can start with a pretty simple example. But right before that, we need to load the quantum framework. We can install the quantum framework, load the quantum framework, and for this case, we need to load also the quantum optimization functionalities. In this case, we'll be using the quantum natural gradient descent, the quantum linear solve, the Fubini-Study metric tensor, and other functions. So let's get started with a single qubit example. So now, as we can see, we need to define first our variational state using two parameters in this case, the parameter theta1 and theta2. So now we want to implement our cost function, and the goal now is to drive this state to the ground state of the Pauli X. So first, let's define the ket and bra from our states, and then implement our cost function like this. In this case, we can see that our cost function is pretty simple, and we can even use complex span because we assume that theta 1 and theta 2, in this case, are real parameters. So now, let's calculate the Fubini study metric tensor. In this case, the Wolfram Quantum Framework already have a function that does this for us. It's called the Fubini study metric tensor. The input for this function is a quantum state that we already find here. This quantum state must have parameters defined. In this case, we define theta 1 and theta 2. And as you can see, this matrix is not that complicated. So now, let's start optimizing. First, we have the quantum natural gradient descent and the gradient descent functions. In this case, for the quantum natural gradient descent function, the first input will be our cost function or the energy function. Now, the second input will be the metric tensor that we will be using. And at the end, we can specify some other options, like the initial point we want to start and the learning rate, eta, that we mentioned it before. For the gradient descent, the logic is almost the same. First, the energy function, and then the initial point. After that, we can add some options like the learning rate. So, as you can see, the quantum natural gradient descent optimization reached the ground state faster. But why this happens? So basically, the quantum variational state that we define have a degeneracy when theta 1 is equal to 0. For example, here there is a formula for this state, and when we replace with theta 1 equals to 0, we find that our state is no longer depends on any parameters. So this is later translated into a singularity when we look into the natural gradient. So let's define first the gradient of our cost function. Now, if we replace in this gradient the theta 1 equals to 0, there is no problem. But if we apply the inverse of the metric tensor that we define into the gradient and then replace the theta 1 value, we find a complex infinity. This is easily visualized in the process of the optimization. As you can see, the regular gradient descent goes straight into the singularity and finds a minimal value. But for the other side, the quantum natural gradient descent process seems to avoid this singularity and find other minimum. Why this happens, and this can be better visualized if we work with the stream plots. The stream plot from the gradient descent tell us that you can reach from the left side of your contour plot to the right side, just going through the singularity. But if you look at the quantum natural gradient descent, you can see that the correction on the gradient won't let us go from one side to another, and this way we will be like avoiding the singularity. So now that we already have the basics of the quantum natural gradient descent and how it works, we can start applying it into a real problem. So now, as I explained before, I will be teaching you guys to apply the quantum natural gradient descent into your own projects. In this case, the project I chose was the quantum linear solver. So let's first talk about the quantum linear solver and then go into a step-by-step. So what's the problem here? Given a matrix M and a vector B, let's find X such that the multiplication between M and X is equals to B. We are basically solving a linear system. So in this case, we have three big steps for this algorithm. First, we have in this first circle A, we have a quantum state X that depends on parameters that is generated by an ansatz circuit. In this case, this quantum state X will represent our X vector of our problem. So we will fit this state into the control multiplexer. Here, the control multiplexer will perform like a multiplication between the matrix and the quantum state X. And the result will be a C state that also depends on the same parameters. We will fit this C state into the classical optimizer that will look to minimize the distance between the C state and the B state. So this will get new parameters that will be fitted into the ansets. And this process will be repeated multiple times until we find that our cost function reaches to 0. So now let's move into a simple example of this. So let's define first a random matrix M and a random vector B. So these, we can use them in the quantum linear solve function that we already have in our Wolfram Quantum Framework. And as you can see, the result is exactly the same as the regular linear solve function that we have in Wolfram Mathematica. So now that we already know how this works, let's go into the step-by-step. So in this case, let's assume you have a quantum circuit in your project. In my case, it will be the circuit from the quantum linear solver. I define the control multiplexer here, and I will load the ansatz from this circuit and the C state that I mentioned before that is resultant from this circuit. So now let's define a cost function as the quantum fidelity. For this, we will use the quantum distance function that we have in our framework and the quantum state B and the C state with the inputs. So let's remember, we need to normalize these values to the process to work. Now, let's calculate the Fubini study metric. So there is a very important point here in which we need to know what state we will be using with the Fubini study metric tensor, because in the previous example, we chose the first state, the first parameterized state that we defined, but in this case, we have an ansatz and a C state, both are variational states. So in this case, we're using the C state because it defines the geometry of our cost function, because our cost function is defined by it. So just keep in mind that, and let's define the metric. Now let's start optimizing. Let's define an initial point using a random real and use the quantum natural gradient descent and the gradient descent functions. So now with this result, we can see a huge difference between the quantum natural gradient descent and the gradient descent. We can even see that in the second step of our optimization for the quantum natural gradient descent, we already reached the solution. And for the gradient descent, it takes way too long, and it's not even close to the solution here. So let's move on and calculate the C state using the optimized parameters and the X state that will be our solution. But right before that, we need to calculate the global phase between B and C. And we also need to denormalize X, because as you remember, in the cost function, we use the normalized vector B and C, and we need to denormalize our X result. And as you can see, we have a pretty close result compared to our regular linear solve. The precision is pretty good. So now we can give a little summary on our presentation. So first, the Wolfram Quantum Framework supports the quantum natural gradient descent method using the Fubini study metric. And we have all those functionalities already available. So we use the Fubini study metric with the quantum natural gradient descent, and we saw that it improved the optimization for our quantum variational algorithms. In particular, we can see that the quantum natural gradient descent and the quantum linear solver fits pretty good. And as you can see, the Fubini study metric tensor, as we explained earlier, is a way to understand the distance between quantum states. And our cost function in the quantum linear solver is quantum distance, the quantum fidelity. So it's the best fit of our metric and cost function. And that's why we can see such an improvement between the variational quantum engage solver cost function that indeed it improved our result, but it's not that good of improvement. But the quantum fidelity improvement is pretty huge. There is a huge gap between them. So for this, thanks you all for your attention. My name is Sebastian Rodriguez, and you can contact me through my email, srodriguez@wolfram.com. These are the reference, and thanks. So if there is any question, you can ask through the chat, and I will be answering them. It's okay, Peter. Thanks for your attention here. So if you have any other question, you can message me through the mail. I will be glad to answer you guys. You can also check the community posts I already made about the quantum linear solver and the quantum natural gradient descent. These are here in the reference. First, we have the tech node, the quantum optimization tech node that I have for all the functionalities, so you can understand how to use them. And you can also check the community posts I have on the multiplexer-based variational quantum linear solver and the natural gradient descent optimization method. So I think there is no more questions. So in case you have any question, please you can email me or write on the community post some comments. It's good to see you guys. I hope you enjoy the tech conference.